Cool. All right. Good morning, everyone. Good to see all of you again. Yeah, so as you may have guessed by the styling of the slides, for the hackathon, we'll be using Polaris. What I'll be doing just quickly is introducing the tasks and introducing giving a quick hands-on demo on how you can get started. After that, I'll pass it on to Johnny to discuss some of the logistics and the schedule for the next 2 days. All right, so as I said, we'll be using Polaris. If you haven't yet, you will be able to create an account by navigating to polarishub.io. Yeah, just give it a quick look. Shouldn't take you very, very long. While you start looking at that, I just want to quickly introduce as well the 2 tasks that we'll be working on. So we'll be focusing on like small molecule predictive modeling. There will be 2 tasks. The first will be on kinase selectivity. So it's about protein ligand interaction, but we added a little twist to it where instead of just predicting the interaction between one protein and a ligand, we'll be predicting the interaction between a protein and and 2 of its mutants. And why is that interesting is because typically in drug discovery, you want to target the mutants while not targeting the wild type protein itself. So yeah, that's that first task. Some details, it's only like 364 molecules. That's small, but you'll find that that's actually a realistically sized data set. So you'll find that maybe fancy deep learning methods don't work as well, or maybe they do work well. You'll really have to play around with some design choices there. We've split the data set using a scaffold split. It's also worth noting that this is a binary classification task, and it's a multitask benchmark. So like I was saying, you're not just predicting against the protein itself, but also against 2 of its mutants. Now, it's a multitask benchmark in that there's multiple things to predict. How you approach that, it's up to you. You could train multiple single task models as well, for example. So we're not imposing any restrictions on the methodology that you use. But given that this is a sort of a dense multitask matrix, it could be interesting to see if multitask methods work in this scenario or not, because there's a lot of information to learn from, especially given the small data set size. And finally, one thing I want to mention is that all the data was generated under consistent conditions. So this was one group that has run all these experiments, and actually that makes us more confident that this is a relatively high quality data set. All right, the other task that we'll be working on is on ADME, right? So that first task is all about making sure that the molecule can actually achieve a therapeutic effect by inhibiting a particular protein, or actually not inhibiting the wild type, but inhibiting its mutants. After we've done that, it's also important that the molecule is actually effective within the human body. So that means there's all these properties which are summarized by ADME or DMPK, and we'll be specifically looking at one of those properties, which is solubility. Solubility is important because, well, it's important to make sure that the molecule can actually dissolve, is that the right word, within the human body and reach the places it needs to be. But it's also important because a lot of assays that we do, they require the molecule to be soluble. So it's a bit of a double importance there. Here, this data, again, has all be consistently generated. In this case, it was done by Blueprint Medicine. And one of the cool things that they did in releasing this data is they made a time split available. So that's something that's typically not available publicly, but now we do have access to that. So that's what we've done here. This is a single task benchmark, and it's also a regression task. So that's a bit different than the task we've seen before. Yes, I'll share the slides, and I will specifically share like a Google collab that will show you how to get started. And we'll do that like right now. Yeah, cool. So if you want to scan this QR code, you'll be able to find your way to a Google collab. I'll also share in Portal. That's probably easiest actually. Cool. Cool. Okay, so if all goes well, you should find yourself at this specific Google Colab. I'll give everyone a time to just get that ready, although I don't see a lot of people typing anymore, so maybe we're good to go. Okay, cool. Okay, okay. Oh. All right. I'll start slowly going through this, so it will take a little bit of time anyways. It's very simple. So we'll be using Polaris to just load the data set, exact same split, but you can then also upload your results to Polaris afterwards so that we can find all those results in a single place and you can compare against your peers. The first thing we need to do is simply install the library. You can do this either through pip or through conda. If you do it through pip, you install polaris-lib. I'll get it started because this always takes a little bit of time. If you do it through conda, you install simply Polaris. After installing it, what we'll need to do is we'll need to authenticate ourselves with the Polaris Hub. The only thing you need for this is an account. So if you don't have an account yet, please create it. I want to show one other thing. Yes. Okay, so if you have an account, you should be able to find yourself to this page. One thing I just want to quickly highlight as we wait for everything to install in the Google Colab is that Polaris uses a ownership model that's very similar to GitHub. So you can actually create organizations. If you want to organize yourself in an organization within your team, it's really simple. Just click the create an organization button. And the cool thing is afterwards, you can upload your results to the organization and only share them with the people that are part of your organization. So while you're hacking away and you don't want to share any of your intermediate results, this is the best way to do that. You can keep your results private and only publish the ones at the end of the hackathon that you feel most confident about. All right, this thing gets in the way. Okay, so now everything has installed successfully. So what we'll do next is we'll log in. And this should be a very easy flow. What it will do is it will show you a link. And what you can do is you can just click that link. And as long as you're logged in, you'll end up on this page where you see an authorization code. You copy that code, you go back to the Google Colab, you enter that code, you hit enter, and that's all you need to do. Now we're logged in, we have authenticated ourselves with the hub, and from here on out, we can download data sets, download benchmarks, but also upload our own data sets, benchmarks, and results. One thing you'll need to do next is to decide the owner. So what is the artifact that Polaris entity that you want to upload your results to? In most cases, this will be the username you've picked for your personal account. However, in some cases, like I was saying before, you might want to use an organization. You can just type in the slug of that organization here, and everything else will work as expected. All right, then for the solubility benchmarks, we'll be using three very basic dependencies. So we'll be using Polaris, Datamol, and NumPy. All of those should be familiar by now. And what we'll see if the Wi-Fi works. It may not. I'm on the right one, I think. Yeah, sure. Conference Wi-Fi. I think it's working, Johnny. We'll try. I think also. Let me try. Yeah. Okay. Conference Wi-Fi, always a little tricky, but yeah. So we'll just be using these three dependencies. With those three dependencies, loading the benchmark is as simple as a single line of code. So it's just Polaris.load benchmark. And in this specific case, you can see I'm already downloading the solubility benchmark that we'll be working with today. It's also very simple to then get the train and test split. And these train and test objects coming out of that, they are data loaders, but they are not framework specific. So whether you're working with Torch or scikit-learn, you'll find that it's very easy to, with a couple lines of code or one line of code, to adopt them to the framework of your choosing. One thing I just want to highlight here, which is not part of the code example you'll find on the website, is that we do allow you to pass in a featureization function. So in this case, I'm simply converting all the smiles within the data set automatically to ECF. That's all that this is doing. And then what I can do is I can just look at the first example within this data set, and we'll see it's a tuple that has both the ECFP fingerprint and the target of interest. So now if we want to train a model, I'm just simply using a random forest model from scikit-learn. You'll see it's really easy. We have this train object, which we can access with the .x attribute, and that's all we need for scikit-learn. So with like just 2 lines of code, we can actually train a random forest model. Similarly, if we then want to actually predict using that model that we've trained, it's again just 1 line of code. We'll give it a bit of time to train. Yes. So it's again just a single line of code. So now this is the 2 steps I just quickly showed, like defining your model, training the model, and predicting the model. I've done this in a very simple way by relying on scikit-learn. It's a good baseline to start with, which what you'll probably find is that over the course of the next days, this doesn't really work in every scenario. So you'll want to try to more complex things. Now that we have those predictions, though, we can submit we can evaluate our predictions using the benchmark object from Polaris. And what this will do is we'll create a results object. And in that results object, we see that there's the metrics, which is the most important part. However, there's also a lot of metadata that you can fill in. So if you're interested in specifying a name or description or tags or user attributes or anything that you think may be helpful in just sharing these results, you can fill that in. For the sake of simplicity, I've just set the name and the description here. And then finally, with 1 line of code, we can simply upload those results to the hub. And if we actually look at them, what we'll see, if it loads, yeah. So what we'll see is this is what those results look like on the hub. One thing worth noting is that they are private, right? If we upload them by default, they are private. That's what I was saying before. If I want to make them public, I can do so with 1 click on the button. This cannot be undone though. So make sure that you do that only for results you actually want to share. You can do as many submissions a day as you want. Although, more philosophically speaking, at that point, you might be overfitting to the test set, but you can do as many submissions as you want. All right, so that's everything for solvability that you need to know. So I hope you'll see it's quite easy to get started. Then for the kinase selectivity one, the process is going to be very similar, but there's a little bit more complexity because it's a multitask benchmark. So what we'll see is if we reload the benchmark with the same line of code, we get the train test split with the same line of code. Again, I'm passing in a featureization function. But now if we look at the first sample in our train set, we'll see that instead of like a single number, what we have is we have a dictionary with each of the different tasks and then the value associated with that task. That means that if you want to train a model on this data, you need to convert that to something the model can work with. So in the case of scikit-learn, instead of having this dictionary, what I want is I want to have a multi-dimensional array. So I'll quickly do that. And then what you can see is I end up with this 2-dimensional array. There's another thing that can happen with multitask data sets. It might be the case that you don't have data for it might be the case that the matrix is somewhat sparse, right? So we have multiple tasks, multiple molecules, but maybe we don't have data for every pair between those two. And that's actually the case that happens here as well. So what you'll have to do is you have to filter out or you have to handle the NaN values in any way. There's multiple ways of doing that. What I'm doing for the sake of simplicity is just filtering it out. And the reason I do that quite confidently is because it's only 1 data point. So I'm okay with losing that one, but there's definitely more complicated things you could be doing. Then again, I just want to train a simple random forest model. In this case, the only thing worth noting is that we use that mask to filter out anything that has NaN values. Otherwise, scikit-learn would crash. And then we can use that model to predict. And you can see we have our 3 predictions. And now there's one more thing we need to do. Because this is a classification model, we don't only need the predictions in terms of the class itself, right? Like whether it's a binary classification. So like we don't just need the 0 or 1 label, but we also need the probability of those two labels because we're working with measures that, with the ROC measure that requires that. So I'll also get the probability. And then what we'll do is we'll have to convert that back to something that Polaris can work with. And the conversion here is just make sure that there is a dictionary with the target as the key and then the predictions as the NumPy array. And then we can again evaluate our predictions. And what you can see is that these predictions are quite terrible. So random forest didn't work great in this case. So that's something you have to try mess around with a little bit to see if you can do better. One thing I do want to highlight is, so what I've done in this case is I've trained a multitask model within like a multitask random forest model. Again, we are not imposing any constraints on the methodology that you use. So you could just as well, which this code example is demonstrating, train multiple single task models and just sort of aggregate those results for your predictions. And then similarly, we can again upload them with 2 lines of code, and you'll again see a very similar page to what you've seen before, where it's private by default, but I can make it public if I want to. And the thing worth noting is that if you want to upload it to a organization, you just have to set the owner attribute, which within this notebook is done automatically because we have this little widget here. But if you don't want to do it within the notebook, you want to do it locally or whatnot, just be aware that that's the variable you need to be set. Cool. Any questions on that? So far, so good. Okay. Oh, yeah. The key, you mean to log in? Yeah, so if you just click this link, there appears a link here. If you click that link, it will bring you. Okay, cool. Any other questions? Yeah, so we use different metrics. So if I scroll all the way down, we use the ROC, the ROC AUC score, for example, but we also use accuracy. And those require different things. So some of them require the probability of a certain class. So essentially the output of your sigmoid, if you're training a neural network model. Other require the class labels themselves. With most common approaches, you'll easily be able to deduct one from the other. Okay, give me a couple more minutes. I'll wrap up quickly. I I like the excitement. Okay, I just wanted to share a couple quick things about Polaris and how it's actually implemented in case you're curious. Maybe that's not the best idea. All right. So for data sets within Polaris, we make the assumption that at the core, it's a tabular data structure where you're storing every row is a data point and every column is a measure for that data point. So for example, you can have a data set that has the smiles and then the homo-lumo gap. This is just simply a pandas data frame. This is something that everyone probably is familiar with. One thing about the Polaris dataset is it doesn't have to be machine learning ready. So you can also have additional information in there that maybe is not as directly relevant to the task, but nevertheless important metadata to have. And what we'll do is we'll annotate each of these columns with an annotation that provides yet again additional metadata. And then we'll annotate the entire dataset as well with additional metadata. There's one interesting question here is like, what do we do with data that doesn't fit nicely within the data frame? For example, if you're thinking about conformance, you have like 3D coordinates. Data frames are not really meant to store that effectively. What we do in this case is we again have that annotation object, but we set the is pointer flag to true. And what that means is we are not actually storing the data set within the data frame itself, but we're storing it somewhere externally. And where do we store it externally? It's in something called ZAR. If you're familiar with HDF5, it's very similar. But what this allows us to do is it allows us to grow to very large data sets quite effectively. So I just want to very quickly tell you about ZAR in case you're interested in adding your own data sets after this hackathon. So ZAR is a format for storing ND arrays. So an ND array can get very big. For example, it could be a terabyte. The cool thing about ZAR is it will chunk that data set. So each of those chunk is, for example, only a gigabyte, and that's already a lot more manageable. And you can randomly access data by only loading the chunk that you need. And then what's even cooler is you can compress that data through ZAR. So we've gone from something that's like 1 terabyte, we can never load it into memory, to something that's maybe only a couple of megabytes, and we can easily load into memory, decompress, access the data we need, and disregard. So what's cool is now we can store these really, really large data sets on the cloud and only pull the pieces that we need to local. Yes. Depends on the compression. No, so it's mostly lossless, but it depends on the compression algorithm that you use. It actually supports a wide variety of compression algorithms. Yeah. Yeah. No, so it of course depends on your data set to see how much compression you can get. But if you think about like storing like raw image data as just a three-dimensional array, saving that as a PNG, you can actually get quite drastic improvements. But it really does depend on the data set and the specific data you have. Yeah. Okay, I just want to say there's more to like about ZAR, but I don't want to get too technical here, but I just think it's a really cool project. If you're working with large scale data sets, give it a look. Okay, so we have a data set. So how do we turn that into a benchmark? So the cool thing is a benchmark within Polaris is just a bunch of metadata. So you can have multiple benchmarks per data set. So what it does specifically is it defines a task, right? So what are the input columns? What are the output columns? And that can be, you predict from the smiles, the homo-lumo gap. But if you know anything about the homo-lumo gap, that's actually a property that depends on the 3D structure of a molecule. So someone else might come in and say, take the exact same data set, but say, I want to formulate a different type of benchmark. I want to use the conformer instead. And it doesn't require you to re-upload the data, right? The data set is still the same data set. It also allows you to define the split. So what's the train set? What's the test set? This is simply done by the indices. That same split today. There's no noise in there. And finally, it defines the metrics. So what are the metrics you need to use to evaluate performance? Yeah, so this is the basic code example that I showed, but the Google Colab is probably a better starting point. If you're interested in adding your own data sets after this, and that data set is stored in another format, such as SDF, we do have a dataset factory class. You can learn about it in the tutorial in more detail, but it allows you to convert something that exists in another format and convert it to something that is compatible with Polaris. Yeah, so the question is, can you just upload a data set without anything, like without a split, without any like benchmarking metrics? Yes, you can. So we made a very explicit decision to split data sets from benchmarks. So benchmarks can think of them as a wrapper of data sets. Cool. Yeah, the thing, this is what I already said this before, but we have this ownership model similar to GitHub. So if you want to organize yourself in an organization, you can upload your results to that organization. And that's it. Yeah. I think in terms of logistics, it will be easy to create an organization for your team, right, that you're working with. You can create as many organizations as you want, so don't feel limited by that. And just upload your results to that team so that we at the end can easily see which team has done best. Okay, that was all that I wanted to say. Then I'll pass it on to Johnny for some logistics.